So in this lesson, we're going to be talking about linear and angular velocity. As you can see, we have a lot of words worth knowing today. Hopefully some of these are somewhat familiar and then some of them will be new. A revolution is the number of times an object spins on an axis. So if you think about the Earth, it makes one full revolution per day, and it makes 365 revolutions per year. That's what a revolution is. A central angle is an angle whose vertex is at the origin. Arc length is determined by this formula, which we'll talk about in a minute. And it's very closely related to the formula that we looked at when we were calculating radians. It's arc length equals theta in radians times the radius itself. And then some other words, which we'll talk about here in a minute, are linear velocity and angular velocity. Linear velocity is the measure of linear displacement of a particle per unit time. So linear means in a straight line. So linear velocity is like movement from one place to the next. How quickly did it move there on that straight line? Whereas angular velocity is the measure of angular displacement. So in a circle, so talking about like how many degrees did it move per unit time. So the difference between angular and linear is the type of movement that's taking place. Is it on a straight line or is it actually an angle? But like I said, we'll talk more about all of these things in just a moment. Let's start with arc length. So to draw a little diagram to kind of demonstrate for you, arc length is this outside portion here, S, and it is associated with the central angle, theta. So central angle is an angle with the vertex in the center, and so the arc length is as big as the central angle that intercepts it. And so that's why they're related to one another in this equation. So the arc length, S, intercepted by the central angle theta, is S equals theta r, where r is the radius, and theta is in radians. So in my last year's notes, I think I like way overdid it with the highlighting. So I'm going to try to refrain this year. But that same diagram that I just drew, I'm going to draw again, so we can get the full visual effect here of what's going on. But all of these measures are related. If you multiply the radius and the angle measure, then that's how big your arc is. So essentially that's what's happening here. The most important part of this whole thing is this formula, though, which allows you to calculate the arc length. So that's what I'm going to highlight. And then another thing that's important is that theta is in radians. You've got to remember that part, because if you accidentally leave it in degrees, then your arc length is not going to be correct. So if they give you something in degrees, then you'll see in a moment we're going to have to convert it. So here's an example problem. A circle has a radius of 10 inches, so r equals 10, and contains a central angle of 120 degrees. Determine the arc length. So we're trying to find S, and we're given theta, but we're given it in degrees. So we need to fill in this formula, S equals theta r. So we've already got the radius of 10 inches, but we need to convert theta before we can actually finish this problem. So let's convert 120 degrees to radians. Try to recall in your mind what's our conversion factor. Hopefully you remember that pi over 180 degrees is our conversion factor. The degrees cancel, and now we just have to reduce this fraction. I think 60 goes into both, so we got 2 pi over 3. And so this is our theta in radian, the invisible unit. And so we can plug that in for our theta now and find that our arc length is multiplying across 20 pi over 3 inches, which is approximately, if you type in your calculator, 20.94 inches. And that's how it's done. If you're given the radius and a central angle, you can find the arc length. All right. So now let's go ahead and talk about the velocities. The reason why we had to talk about arc length is sometimes you have to calculate this before you can find either of the velocities.